Okay. Hi everyone. So I'm going to talk about our ongoing formalization of nominal sets in the CoqPL system. So, as I assume that everyone here sometimes or other have to deal with manually with binders, and the problem is that we have to for every definition and theorem we have to deal with alpha equivalence, and this could be really cumbersome and error prone. Like for example, in this definition of the substitution for the lambda calculus, and most of the definitions we have to is trying to deal with correctly with the alpha equivalence. In pen and paper proofs, we have devices like a Barendek variable convention to overcome this, because we work with a class of alpha equivalence terms. And we can differentiate every bound variables from free variables. We have many representations to do this kind of work, like with the Brown indexes or locally nameless higher order abstract syntax. But these representations, it's when you try to do comparison with your formal proofs and informal the formal proofs, it's too different, so sometimes is too hard to try to assimilate one another. But the nominal approach, one of the selling factors of this representation is that our proofs, formal proofs, is quite similar to the informal pen and paper proofs. The nominal sets, that's the foundation of the nominal theory. It provides us with tools for reason about abstract syntax with bound names. And we need only one extra definition information on our syntax, on our development. That's the action of name permutation. Here, I am trying to say what is a name. It could be anything I am treating as an atomic structure, but could be any sets could be any set infinite with decidable equality. This name permutation we define simple as a swap operation. That is a permutation when we compare three names. And our permutation will be defined as a composition of these swap operations. And to act this permutation over our syntax, we define our group action. It's just a normal function we call action that receives a group. In our case, it would be a permutation group, and it needs to satisfy the group action properties. As an example, in the lambda calculus, here how we could do this implementation of this action over the lambda terms, such that we can satisfy this property of the group action. But this is just not a different way of do the renaming. It has really good properties. It's really simpler to implement and has a better behavior if we compare to the standard substitutions methods. This better behavior that we're really interested in is that the action of name permutation, it doesn't capture free variables. Here, one example to the side. But more importantly, it defines a generic notion of name dependence and independence. Here we will call as support and freshness condition. We say support is just a subset of names, a finite subset of names. And we say that it supports an element of a set with a name permutation action. If for any permutation, if this permutation fixes all the names in this subset of names, the permutations should fix our term. We can find the smallest support that is basically the intersection of all supports of X. But here in this work, we'll use a different definition of support, but equivalent, using swap operations defining here. As an example, in the support function, the support definition, it varies depending on how we are working. So, for example, in the lambda calculus with syntactic equality, the smallest support is the set of all variables of some given term. And when we are working with alpha equivalence, the smallest support is equivalent to the set of free variables of the term of the lambda calculus. So the smallest support usually is the set of the free variables when we work modulo alpha equivalence. And so, given support, we can define nominal set is just a set with a name permutation action, which all elements are finitely supported. And so we speak about freshness, and freshness we can define pretty easily from nominal sets. So given a nominal set X, we say that a name is fresh from an element of this set, and here we denote by this symbol, saying A is fresh in X, if A doesn't belong to the smallest support of X. So, as I have shown, nominal set is provide us with tools, great tools to work with binders. And simple and uniform meta theory, which is based on this only name permutation that we have to define. And with this name permutation, we can define the set of free variables, the lambda abstraction, and induction and recursion principles modulo alpha equivalences. So, when we are trying to implement nominal sets in the Coq proof assistant, what issues we find? So the theory that I just present here is classical, because some of the aspects of the nominal theory is not constructive. Mainly the smallest support, it doesn't always exist, but principally it can lead to the derivation of the weak limited principle of omniscience. Instead of working with with the smallest support, we work with some non-unique support, such that the smallest support is contained in this support. The nominal set of functions and name abstractions that I will not discuss here is another factor in the implementation of nominal set, is that when we try to define the nominal sets of functions in the Coq, we need the axiom of functional extensionality to be able to prove property about the set and the name abstractions. So since we want a fully constructive development, we have to resort to the use of setoids through the whole development. Our work is not original. It's basically a port of the work done by Chowdhury in Agda, entitled Constructive Representation of Nominal Set. But in his work, Chowdhury faced serious problems related to the use of setoids. Setoids made of proofs even more verbose. And it becomes unwieldy when one had to simultaneously manipulate several setoids. So in our implementation in the Coq proof system, I propose we use a type class hierarchy to represent nominal sets. Our development will be using Coq version 8.14 with the help of the STD++ library, because it provides better support for type classes. So to define first what we mean to our representation of permutation, we'll try to we are defining permutations as just a list of pair of names, and every pair we will be representing our swap operation. As I have said, swap operation is pretty simple to implement in Coq. And so to really verify that our representation really forms a group, because we'll try to apply to an action of permutation group later, we'll define our class, our first class, called group, that here we are using the unbundled approach. We have for each group operation, we define our one specific class to represent this operation. And in the class itself group, we bundle every property that we want, such as the group properties and the rewriting lemmas. So one downside of this representation of permutation is that it's not unique. So we need a representation, equivalence definition for our permutation. And so, as I have said, we have to bundle our rewriting lemma inside our class, and we can easily show this representation respect the group properties, with the neutral element of the permutation being represented as the empty list. The binary operator is just the concatenation of the two lists. And one biggest advantage of this representation is that we can easily compute the inverse permutation just by doing the reverse of the list. And so now we define our group action class. We basically follow the same approach done in the previous class. Here, the difference is that we parameterize explicitly our group action to a certain group that later we specialize to our name permutation. But unfortunately, sometimes with this representation, Coq couldn't automatically resolve the problem rewrite lemmas with a bunch of tactic failures, setoid rewrite failed, where we can't satisfy the following constraint, which was really hard to debug. But we could manage to do this the rewrite manually. So we don't know exactly what is going wrong with this representation. To solve this, we merged both classes in one class only. That is to represent the permutation type, as we call. That is just a type with ID of a notion of action of permutation. With that class, we can finally show our nominal type class. As I have said here, we are working with some non-unique support that has to be manually specified by the user as in the support class. But first, the user has to manually verify that this definition of support really have what we're looking for the support property. So about freshness, we can't use the classical freshness definition for some support, as I show here in the green equation, because freshness must preserve the equivariance property. That is basically that the property stays the same even if you do a permutation within both sides of the freshness property, which is not always true when you work with some support. Instead, what Chowdhury does that we basically translate to the Coq, it's use the alternative definition provided by Pitts in his development, the idea of the freshness quantifier. But since we can't, since we need the support of the underlying the Coq from the Coq to specify this freshness quantifier, we use another alternative but equivalent definition that's based on the existence of a new name. So we can say that if a name A is fresh in an element from a nominal set X, if we can basically show some new name B that doesn't belong to the support, and in that it preserves it fixes the permutation action. With this definition, we can show that it's really equivalent. And with these definitions, too, we can define an easy form to find a fresh name. To show that our frame is a new name is really fresh, we just need to show that it doesn't belong to the support. And we can do that by using SDPP freshness definition. We pass some subset of a set, and this operation can easily find a new name that doesn't belong to its set. So we can show that it doesn't belong to it's fresh from the disturb. So, but how our proofs look in practice? As I said, we try to use setoid and setoid rewriting in our development, such that setoid could be such a burden for us. As you can see, most of our proofs is basically a chain of rewriting, where in this, as an example here, we have multiple rewritings involving multiple setoids, group, permutation type, and nominal setoids, where there's no explicit setoid inside. So our proofs become much more shorter. It's really easy to do, and in most of the cases, it's quite similar to the informal proofs from pen and paper. So, concluding my presentation, we report our work in progress formalization of constructive nominal sets in Coq. Right now, it's basically apart from Chowdhury's implementation in Agda, but one change or something that we are changing in the future is that to further develop its implementation, Chowdhury uses category theory, but we are trying to use nominal abstract syntax to derive the more complex properties. What is done right now? So we've done what is done. Nominal sets support freshness and its general properties. It's done. What we are working on right now. It's the nominal set of functions. Mainly, we are trying to provide a better user interface for it, and in the definition of name abstractions. And so about the type classes plus setoid rewrite is really a randy tool in the development. It leads to shorter proofs. Most of our proofs is just a chain of rewriting lemmas, and don't have to explicitly deal with setoid in most cases. And the most proofs are quite similar to the pen and paper or informal proofs. As I have said, unless something goes wrong, because it's really difficult to try to debug what's going wrong in the rewriting tactics, which leads to a lot of the redesigns and tweakings in our hierarchies. I have said we needed to do this tweaking to be able to progress with our development. And so for the future, what we are trying to do is automation. We are focusing on automation of this derivation of the nominal set. As I've said, given our idea is that given a syntax or inductive type for an abstract syntax, we can derive the action. In most cases, it's possible to derive the support and the alpha equivalence and other properties. But we will mainly focus on the derivation of the alpha structure and induction recursion combinator. This combinator, the idea is that we can work with modulo alpha equivalence in our proofs. And for this, we are assessing our options for plugin development. Right now, we are studying our options. This is MetaCoq, mainly MetaCoq in LP, and trying to figure out what we can do with LTAC2. And so, thank you. I really appreciate your attention. If someone is interested in our development, it's in the GitHub repository. And thank you. I'm waiting for your questions.
Thank you, Fabricio. Do we have any questions from the room? Leo has a question.
Hi, thank you. That was a very interesting talk. I had a very broad question, which is, say I design a new language, and I'm wondering what kind of property that I want to prove would tell me that I want to use nominal sets.
So the great things about nominal set is that the main aspect what we are trying to do is the derivation of the alpha structural induction and combinator. With this combinator, it's really easy to try to prove properties related to when we involve a lot of alpha equivalence properties, because it's really like if you're using the body track variable convention in your proof, because you have a guarantee that every bound variables will be different from the free variables. What's more, you have this strong hypothesis regarding your bounding variables. If you in some of your development, like I said, if you could, okay, I really need some kind of substitution operator, you could use the action for defining it, because you can use the freshness properties to try to come up with a really new name in your syntax. But I think the real what nominal really shine about is when you try to formalize something, because it's not really different from what you do in the pen and paper. in your informal development. But for implementations, for language permutation, I really don't know what. One aspect that you could do is, like I said, do the substitution. It's really hard to do it right in the first time. Then and the nominal you could benefit from the nominal because defining swap operations is a lot easier than defining the substitutions.
Okay, thank you.